Hello, my name is Maria.
And I'm Fernanda. We're students from Tec de Monterrey Campus Estado de Mexico. Today we will present the problem addressed in this project, the methodology we followed, the control strategy we implement, and the final results. Motors must accurately follow reference signals to achieve stable and predictable motion. For this reason, we implemented a motor speed control system using ROS2 and a microcontroller. The objective is to regulate motor velocity using encoder feedback and a PI controller, allowing the motor to follow different reference signals. The system is based on ROS2 nodes communicating through topics, while the hardware interface uses micro-ROS on the ESP32, which controls the motor via PWM and reads encoder measurements.
To solve the problem, we performed 5 main experiments. The first one was static model identification. The purpose is to study the relationship between the input and output once the system has reached a steady state. We applied 100 operating points covering a command interval from -2 to 2 with increments of 0.04. For each input value, we averaged 50 measurements after the motor reached steady state. From this experiment, we observed that the motor represents a dead zone approximately between -0.04 and 0.04, where it does not generate enough torque to move. Saturation was reached at approximately 283 revolutions per minute. No significant hysteresis was observed, and the system showed good symmetry. From the linear zone, which spans from 0.08 to 0.9, we obtained the amplitude of 0.4 and an offset of 0.5. These values were essential inputs for all subsystems.
The second experiment was frequency response identification. This analysis studies how system behaves at a steady state across different frequencies. We applied a sinusoidal input where the offset was 0.5 and the amplitude was 0.4, the values from the previous stage. For each frequency, we calculated the gain in decibels and the phase in radians to build the Bode diagram. From the Bode plot, we identified a cutoff frequency of 7.96 radians per second, which defines the maximum frequency at which the motor can properly follow a reference. This gave us a first-order transfer function that is shown in the yellow box.
The third experiment was dynamic model identification using a step response. The objective is to transition between two operating points, both within the linear zone. We applied a step from 0.1 to 0.6, an amplitude of 0.4, and analyzed the output response. We used the Smith method, which approximates the system as a first-order model with time delay. As shown in the graph, we used specific response points to estimate the time constant and delay. The result was the transfer function in yellow. As well, the gain and time constant matches the probability of the.
With the identified model, we designed the controller. We select a PI controller, proportional cross integral, where the proportional term improves the response speed and the integral term eliminates a steady state error. We use the Schoenhorst-Reswick method from 1952 because we know that it is more stable than Ziegler and Nichols method.
We calculate the theoretical gains in radians per second. After converting them to revolutions per minute, the gains are Kp equals 0.35 and Ki equals 0.26, which produce a significantly more accurate response on the real hardware. For the sampling frequency, we apply the Castaño 2020 criterion, which is based on the system setting time, which this gave us a valid range from 83.3 Hz to 158.7 Hz, and we selected 125 Hz. We implemented an anti-wind-up mechanism where the integrator only accumulates when the control output is within the valid range, preventing integral wind-up during saturation.
The controller was implemented within the ROS2 architecture. A signal generation node runs on the external computer and publishes the reference signal to the setpoint topic. The ESP32 subscribes to this topic and executes the PI control loop at the selected sampling rate. The node can generate steps, sinusoidal, cosine, square, and triangular signals. All signal parameters are configurable at runtime through a Jamal parameter file. The controller gains Kp and Ki can also be adjusted dynamically via the topics, enabling live tuning during experiments. Also, a low-pass EMA filter was applied to the encoder speed signal to reduce measurement noise. Also, due to the noise of the encoder, derivative action wasn't necessary as it would only amplify the filter signal's residual noise.
And this is our motor with the static and theoretical values. This is our motor with fine-tuning variables. This is, for example, a sinusoidal signal and how our motor behaves. So this is a square signal, and this is the behavior of the motor. And if I apply some perturbation, it's in the motor, well, in the signal, but the controller makes it stay stable. Finally, we perform fine-tuning of the controller gains to improve performance under real operating conditions. Some issues or limitations presented were encoder noise, PWM reversion, and communication delays between ROS2 and the hardware. The motor followed successfully step, square, and sinusoidal signals with stable and predictable behavior. There are some delays due to the mechanical dynamics of the motor and communication latency between software and hardware layers.
In conclusion, this project demonstrates how ROS2 can be integrated with embedded systems to implement closed-loop motor control. By combining system identification, control theory, and robotic middleware, we successfully regulated motor velocity and analyzed its dynamic behavior. Other advantage of using ROS2 is that the modular architecture allows us to easy integration of the signal generation, control computation, and hardware communication. A limitation can be that the communication latency between the ROS2 nodes and the embedded hardware, which